So I'd like to do another proof by induction for you now. This one involving a sum over a sequence. So it's similar to the ones that we've done involving 1, 2, 3, 4, 5 and also the one involving the odd numbers. And in this example, I've decided to choose the even numbers just for a change. And I'd like to show that the sum of the first n elements of this sequence is equal to n squared plus n, where n is a member of n1. So one of the first things that I'm going to need to do is to get a general formula for the elements of this sequence. And since we're using n as a member of n1, this time I'm going to start my numbering at 1. So this is the first element, the second element, the third element, the fourth element. So the general formula of the, let's say, the kth term in the sequence is 2k. So the first term is 2, the second term is 4, the third term is 6, and so on. What I want to do is to show that the sum of the first n terms of the sequence is equal to n squared plus n. So in other words, if I add up the first n elements of this sequence here, what will I get? And the statement says it's going to be n squared plus n. So again, base case. And I reckon that the smallest value for which this makes some kind of sense is n equals 1. So we will just say, okay, so the formula says, so the sum of the first element, so the sum of the first one elements of this series, well, that's 2. The formula, n squared plus n, is going to be equal to, well, it's 1 squared plus 1, and that's equal to 2 as well. So for the base case, it works, and that was simple enough. Now we assume true for n is equal to k. So I should have said here we're doing the inductive case. Inductive case. Put that in there. So the inductive case, we're assuming true for n is equal to k, just some arbitrary value. So that means that the sum is equal to 2 plus 4 plus 6 plus 8 ... up to and including the kth element. Well, the kth element of this series is 2k. So 2, 4, 6, 8, and then eventually I get up to the kth element. So element k of this ... is going to be 2k. That's the kth element there. So that's what I've got here. I've got all of these added up to and including that element there. And the formula says that that is going to be equal to k squared plus k. And we're allowed to assume that true. So now we have to prove for n is equal to k plus 1. In other words, the next case, but we're allowed to assume that this is true. So let's write it down. So the sum now, let's write the k plus 1th element, the next one. What's that going to be? Well, it's going to be 2 of k plus 1. That's the next element after k. I'll put ... to show that they do go on after that even. So the sum is going to be 2 plus 4 plus 6 plus 8 plus ... plus, well, we've got the 2k element, but now we're adding up the first k plus 1 elements. All of these right up to this one. So we need to add in that element as well. That's the extra one, 2 times k plus 1. And the statement says that that's going to be equal to k plus 1 squared plus k plus 1. And I'll put a question mark over that because we haven't proven that that's true yet. We think it might be, but it might not be, and therefore that's what we've got to try and prove. Okay, so let's try and prove it. I'll get my other colour Sharpie because now we're going to use the assumption. So all of this lot here, all of that lot there, I see also appearing here. Goodness me. So that is something that's very useful. At the moment, I can't prove that this is equal to this because this term here, well, it's huge and it's got a ... in it even, but it's exactly the same as that. So I can use, I'm going to get a purple Sharpie just for a change. There we go. Oh, it's kind of pink actually. There we go. Hopefully you can see that this is a different colour. I'm going to substitute that in for that thing there. So let's do it. So the sum, if I do this substitution, what I'll actually get is k squared plus k, that's me using that, plus 2k plus 1. Sorry, 2k plus 2, that's me multiplying out that bracket there. So I've got the k squared plus k from there. I'll put that in the slightly pinky box there. And then the 2k plus 2, let me put that in a blue box. In fact, a lighter blue box. Got a lot of Sharpies. Oh, that's not a Sharpie. That's a lighter blue one. There we go. That's a lighter blue box there. And that comes there. So that's that. And this thing is that there. Now the question mark is that equal to, well, let's multiply out this side and see what that comes to. So that's going to be k squared plus 2k plus 1. That's me just multiplying out the bracket there. Plus k plus 1. Now, let's see if we can make these the same. So let's draw our terms together. So we've got k squared, and then we've got 3k plus 2 on that side. And the question is it going to be the same as this side? We've got k squared plus 3k plus 2. That means that assuming that it's true for n equals k, I have now proved that it is true for k plus 1. So the inductive case k implies k plus 1 is true. Therefore, the statement is true by induction. And I finish my proof with the little box there. The tombstone of smugness, meaning that I've now finished.